Good morning, afternoon, or evening. I'm Frank van Diggelen of the ION, which exists to promote the art and science of navigation. The ION is heavily influenced by GPS and GNSS, but one of our goals is to put navigation back into the ION, and towards that end, we'll be bringing you webinars such as this one, focusing on navigation topics of general interest. You may be interested to know that this is our most popular webinar ever. And if you enjoy it, but your friends, colleagues, or families can't make it, it will be available on all platforms afterwards. You can find it later on ion.org, our website, on our YouTube channel, or other typical video outlets. If you work in any type of navigation, whether in space or on Earth, there is no better professional organization and network than the ION. There is nothing better you can do for your career today than sign up for membership of this organization, because this is where you will find your future colleagues, mentors, and employers. So if you're not already a member, go to ion.org later today and sign up. Now, our annual GNSS event, ION GNSS Plus, is coming up on September 20th in St. Louis, Missouri. This will be our first international gathering in 20 months. So it's always a great in-person event where you can meet the people who literally built GPS and all the GNSSs, such as Galileo, etc. So if you're getting tired of being stuck at home, come and join us. I hope to see you there. Now, onto the main event. We're privileged to have Dr. Gerhard Kruizinga from NASA to tell us how you navigate to Mars. First, some logistics. The way we're going to run the webinar is Dr. Kruizinga will talk for about 40 minutes. And during this time, you can submit questions using the Zoom Q&A button, which is highlighted on this slide. Also, if you have suggestions, topics, or speakers that you think would be good for future such webinars, use this Q&A button to submit them to us. And if you think of them later, you can email from our website. Back to the webinar. Once Dr. Kruizinga has finished his talk, I will ask the submitted questions during the last 15 minutes or so. Remember, there's a correlation between the shortness of questions and the likelihood of their being asked. Dr. Kruizinga is the navigation team chief for NASA's Jet Propulsion Lab. From July of 2020 to February of this year, he and his team successfully guided the Perseverance Rover from Cape Canaveral, Florida, to Jezero Crater, Mars. Now, that's what I call navigating. NASA remains the only organization ever to have landed spacecraft successfully and softly on Mars. And so it's a great thrill to get a little insight into how they do it. Dr. Kruizinga originally hails from the Netherlands, where he did his undergraduate degree at the Technical University Delft. Then he came to the US for his PhD in aerospace engineering at the University of Texas at Austin. He has worked at JPL for 23 years on many landmark projects, including TOPEX Poseidon, JASON, and GRACE. These programs contribute to oceanography and mapping of gravity fields, and in turn, our ability to model orbits, such as for GNSS. So even if you are not familiar with these programs, you are a beneficiary of them anytime you use GNSS. The Perseverance rover is Dr. Kruizinga's fourth lander on Mars. And so now I'm very excited to hand over to him to tell us how you get from Earth to Mars.
Thank you very much, Frank. Just a voice check. Can you hear me? All right. Let me start sharing my screen. All right, so well, thank you very much for that very nice introduction. So as I said, I will be talking today about the navigation from all the way from Earth to Mars for the Mars 2020 rover. So with that, let me actually, that did not work. Okay, so I wanted to start with this really, I would say almost now iconic image, which is the landing of the actual Perseverance rover on Mars a few meters above the ground, and you can see actually the dust already, the kind of like moving away in a sheath, and it's about to land. And this actually for us is a very special moment, because until now, as you heard, this is my 4th lander on Mars, but it's the first time that we actually could see it land, even though it was after the fact when it actually transmitted, but had quite a few cameras on board to actually show us where we were actually landing. And it was just quite spectacular to see, and that it all worked so well as we expected. But also for us navigators, actually, the landing is a very special place, because actually it's where we start actually our planning to actually fly to Mars. We actually kind of do actually cheat. We look in the back of the book at the answer and then work our way backwards and get actually a navigation solution that makes it work so that we can actually land on Mars, which is not always a lot of other problems that you would do that way. But here we actually start with the answer. And so what is the answer actually in this case? So, I'm sure you heard that we have something what's called entry, descent, and landing. And that basically, that team is actually responsible for landing, basically once we are hitting the atmosphere to all the way to the ground. And what they do actually is they give us actually what they call a reference trajectory, or basically how are they going to fly through the atmosphere. So if you work your way back from where you want to land, you can actually go all the way back to the beginning, and you can actually, that's where, they say, we would like you to end up here. And the way I kind of think of it is kind of like a garden hose. If you have a 700-kilometer long garden hose, you kind of attach it here to Earth, you kind of shave it in this form, and you put it here, and then basically what the EDL folks want us to actually do is to actually fly into that tube, if you want, without actually hitting the walls of that tube. And also, because Mars is rotating, we can only actually land once every Martian day. It's not like you can arrive anytime and, oh, we're going to land. No, we actually have to, so that this opening is right at the right moment. And to give you an idea, we have to fly in this tube, and it's about 10 kilometers in diameter, but we're coming in at a velocity of 5.5 kilometers per second. And this is after we've traveled about 470 million kilometers from Earth. So it's quite a feat to actually hit that rotating tube on Mars to actually did it. And then once we actually get close, actually they become even more demanding. They said, kind of get us somewhere in this circle, but actually we want to know much better where we are in this circle. And that's actually our main goal, actually, is to provide the best knowledge to actually land. And the reason is, there's no GPS on Mars, like Frank just said. It's on Earth, we always think on navigation, you have GPS. No GPS on Mars. So we need to somehow tell the onboard computer, you are now at this position with this velocity, and now land yourself. So the update, that parameter update, is very important. It is one of our main goals for navigation actually to Mars, and actually land safely on Mars. So just to give you an idea, that 10-kilometer tube, to get an idea, is about, on Earth, if you would actually hit a golf ball, you would have to hit a target about 18,000 kilometers away with a 10-centimeter diameter. And if you would do that, if you would tee off in New York, you could actually, what we did, it's the equivalent of actually hitting a golf hole-in-one in Perth, Australia. You can also see that we have actually 5 actual what we call trajectory correction maneuvers. It's basically, this is not a hole-in-one, it's really a par 5. We get 5 times a chance to actually change our correction slightly, but still hitting this hole in 10 centimeters in Australia. So just to give you an idea of the challenge of actually doing this particular navigation job. So here's then a kind of a little bit more formally what our requirements are. And so the first one is that the entry flight path angle is the angle that we hit the atmosphere with, has to be within 0.2 degrees uncertainty. And the reason is, if you come into steep, you burn up. If you come into shallow, you actually bounce off. So there's a minus 15.5 degree angle requirement, but we have to hit that with an uncertainty of 0.2 degrees, 3 sigma. Then cross track, basically in the direction that perpendicular to flight, we have to be within 5 kilometers. And so you can see now here that actually our opening of this is basically the opening of the tube. It's not really circular, it's more like a rectangle, and I'll show you that a little bit later. And then the second point is here, that's our second requirement, is the accuracy. So we have to determine the position and the velocity to 2.8 kilometers and 2.0 meters per second in velocity. And this is really the most important thing, is that we provide with the most accurate state on board. So this is basically that little green circle that you just saw inside the opening of the tube. Then another thing is, you would think, well, you go straight to Mars. We're not allowed to. And the reason is, the upper stage of the launch vehicle, once it actually stops the engine, it will just fly basically with the rover to Mars as well. And we don't want that to impact, because it hasn't been cleaned for planetary protection reason. So the requirement is actually, we cannot hit Mars for the probability of hitting Mars for at least 50 years. It has to be less than 0.1 0.01%. And so because of that, we're biasing actually. So we're not aiming for Mars directly. Another reason is we cannot aim directly at Mars is because if we, let's say, fail one day out after launch, we do not want to hit Mars with a spacecraft that cannot be controlled or we can do anything. Even though it's designed to go to Mars, we don't want to do that. So there is also the probability that we have a failure of the spacecraft, and hitting Mars has to be less than 1%. And the other thing is also very important for anybody, you know, when you drive your car somewhere, you can only bring so much gas with you. In our case, we have 45 kilograms of propellant that we can use for those correction maneuvers to actually get us to the right opening of the tube, or basically our delivery target. So before I go on, I just want to say a little bit, you know, a lot of people here are probably very familiar with the navigation process, but I just want to say a few words. So how does it really work? So basically on the left side here is you have a real world. You have our spacecraft traveling to planets. And on the right-hand side is actually our model of that world. And what you basically do is you take observations and then you compare those observations with what we predict from our models. And there's basically two parts to it. Is what we call a dynamic model, which is basically things what affect the motion, the forces acting on the spacecraft. And of course, you also have to model your measurements because, you know, you're on the Earth, it's rotating, it's going around the sun. Also, we need to know where Mars is. So it's a very large model that we have. And what we do basically is you take those measurements, you compare that to what you actually measure. And then basically what you use is you use least squares, very simply, to drive those residuals small, like we do in GPS, so that we can have the best model. And then if we need to update our model, we will. If we're not quite there yet, then we update it and we iterate until we do. Once you have a solution, where now you know I'm here, I'm gonna go here, then we actually check, well, are we actually going to the tube or whatever target we have? And if we don't, we actually then design an extra maneuver to actually to link up to the spacecraft so that we can actually maneuver it to another new place. And so that's basically in a nutshell. And this is very old. This was published in 1976. Really, things haven't changed that much. So how do we do this? So we're using actually the Deep Space Network, which is basically 3 complexes with really big antennas, 34 meters and 70-meter antennas. And we have 3 complexes. One is in Canberra, Australia. Another one is in Goldstone here in the US. And then another is in Madrid. And they're about spaced about 120 degrees apart approximately, so that we can continuously track the spacecraft if we need to. Now, for most navigation jobs, you always kind of look ahead. You know, you're looking ahead, where are you going? And in our case, you know, we need to go to Mars, 470 million kilometers away. However, we don't do that in this case. There's nothing that senses Mars at all. So we actually always look back at Earth. We're basically navigating through the rear view mirror continuously. And what that means is we need to really know very well, and here you see Mars, we need to predict that Mars is just at the right time when you hit your target where you actually get there. And basically, as I said, we don't sense Mars. We kind of sense Mars at the very end. About 20 hours before we land, the Mars gravity well actually starts curving the trajectory. But by that time, if you need to do something about it in terms you're not on the right course, it's most probably too late. That's why we really rely on a very accurate model for where Mars actually is, one of the models that we have. And I'll show you a little bit later how we actually checked that Mars really was what we thought it was going to be. So what kind of tracking do we get from the DSN? So we get Doppler data and ranging data. Those are the 2 tracking types. We have another one that I'll talk about in a second. And we basically have two-way Doppler. And the first thing, two-way Doppler is basically measuring the velocity from the station to the spacecraft, but using, in GPS, we generally use phase, but, we use actually the first derivative, basically the frequency. And that frequency is then measured, but you can see, Earth, as I said already, is on a rotating Earth. The Earth is rotating around the sun. There's other forces acting on the spacecraft. So there's a lot of things that we need to model in order to use this measurement. And to give you an idea, so first of all, for the measurements, we actually go to the troposphere and the ionosphere, just like GPS, we have to correct for that. Also, the Earth orientation, which determines where the actual station is. And also, we need to know where Mars is in the orbit around the sun. And to give you an idea of our accuracy, we're using actually 0.1 millimeters per second data weight for our Doppler data. And ranging is more straightforward. It's just computing the two-way range. You just measure the turnaround light time to actually measure the range. It's a little bit more complicated than that. And we're not using exactly kind of the technique that's used for GPS, but it's similar. And we get a range measurement out of it. And we use actually a 3-meter weight on that measurement. And the reason is There's also other, besides troposphere and ionosphere, there's also solar plasma, for instance. You'll see a little bit later, we see some variations due to that. Then, so you can see here, we're measuring the range in the Doppler, and that gives you very accurate information in the direction to Earth. And you can see here's the uncertainty ellipse, and we actually in our team call it the pancake because it's really thin in the direction of the line of sight to Earth, but quite big in perpendicular to that, in basically the declination and in the right ascension of that position. So we need actually another measurement that really tells us something about in that direction. And we use for that basically something called the delta VLBI. And in our case, we're using, again, this is a very old picture, but we're using actually the delta difference one-way range. Basically what you do is you listen with two stations, for instance, Canberra and Goldstone, to the spacecraft, and they have a special tone. Then you listen for a while to a quasar, and then you can subtract those measurements. And by doing that, like in GPS, with your one-way differencing, you can difference out a lot of errors. But on top of that, you can actually difference then those two measurements again, and that's what that different delta difference to delta DOR is. And what it basically tells us is like, what is the angular distance in the direction of what is that called? The baseline where it is in the sky, how much you are off. And this measurement actually tells us actually where we are in that there's the declination and the right ascension. And at Mars, when we landed, this was about 500 meters. So you get about a 500 meter measurement for that. And this actually turns out to be the enabling measurement that allows us to do this landing that accurately. If we didn't have delta DOR, and I'll show you that later, you could not land, that you could not decide early enough if you were on the right track or not. Eventually you will, but by that time it's too late. So we know we need to get all that tracking data from the DSN, and of course we need to have a trajectory. And so one of the first things we do is we have our mission designers come up with a trajectory, and this shows the trajectory, the heliocentric trajectory from Earth to Mars, and it shows it for the day of the first day that we had actually our window that we could launch was on the 17th of July. And then basically we determine how much measurements do we need for, to do accurate determination where we are for the TCMs, also that we can meet our knowledge requirements in the end. And in this case, as I said, the launch period was we had about a month, but we launched about in the middle of it because there were some problems with the launch vehicle that delayed our launch. So that's why we launched on July 30th. All right. I'm not going to go too much over this. This basically shows you all the measurements that we get, but you can see for the first 30 days, we're getting continuously Doppler in range. And then it drops down in the middle of the mission. But once we are 45 days out, we get again continuous all the way to landing. But you can see here that the delta DOR measurements, we're getting a lot more towards the end. And of course, as I said, it's really these two sessions a day that really allow us to actually land that accurately on Mars. So what was our strategy actually? So the first thing is we have to, as I said, we cannot aim at Mars directly. So the first thing is we need to remove that injection bias that we introduced on purpose. And then also, because we cannot right away target to Mars, because we don't want to hit Mars when the spacecraft is not working anymore. So we also have to keep targeting from Mars away. And that's basically why TCM2 was not already targeting to actually the entry point. We actually targeted away from it. Then TCM3, we were finally allowed to actually target to the actual atmospheric interface. And you can see here, that's basically what we did. And you see, we had other maneuvers planned, and they were mainly there just to correct any errors from TCM3 and any OD errors. But you can see I grayed them all out because they were not needed. We hit with the first time we targeted, we right away hit the target, which was a little bit lucky, and I'll show you a little bit why that was. So as far as the spacecraft is actually what we call a spinner. Basically, it spins as it flies to Mars, and it's basically spinning about the spin axis, what you see here, about 2 rotations per minute. And that has great benefits to navigation because, first of all, because the attitude control, there's virtually no attitude control. So we don't get any little thrusting going on that moves the spacecraft off while we fly. We only maybe thrust well once every 1 or 2 weeks. So because of that, we can really predict very well. I also call this spacecraft the Cadillac because of it, because it predicts very well. And I'll show you a little bit later how well it predicts. It really, it almost looked like we were fitting the data. That's how well it predicted. Now, there's several parts to the spacecraft, but the part that's really relevant for navigation is the cruise stage, this upper part here. You can see here at the bottom here, these white boxes here are actually radiators for heat. But here are our thrusters. We use these thrusters to actually maneuver the spacecraft and to turn the spacecraft so that we can maintain the solar panels at the sun and also our antennas in the direction of the Earth. Then here you can, of course, see the back shell, the descent stage, basically the jetpack for the rover as it goes down for the last couple of 100 meters, and then actually here the heat shield. So as I said, this is really a very clean spacecraft to fly. I've flown other missions where we have lots of thrusting, which makes things a lot harder to do. So as far as what do we all need to model, I told you we have quite an extensive model, and there's probably a lot more to say here, but I only want to hit the highlights here. So first, we need to know what the planets are, and not just the planet where they are, but also their gravity, because as we fly, even to Mars, Venus, Jupiter are still affecting our trajectory if you want to do a high accuracy navigation. Then we have to model solar radiation pressure. I'm sure people that work on GPS satellites are very familiar with this. And because we're spinning, a lot of the actual radiation forces actually average out. So we mainly only get forces acting in the direction of the spin axis, which is a nice feature too that helps really for the accuracy. Also, we have actually a little nuclear thermoelectric generator on board, which generates heat. That heat actually comes out of the spacecraft, and again, because it's spinning, it only comes out in the direction of the spin axis, and we can really observe it. It's very small. It's only at the order of 10 to the minus 12 kilometers per second squared, but we can see it. It does have an effect. Of course, spacecraft have outgassing it, particularly after launch, the first 2 weeks, but also for instance, when they were heating up the thrusters for the lander, we saw outgassing from that as well as we went to Mars. As I said, we have to actually control the attitude of the spacecraft while we fly to Mars once or twice a week. But even though the thrusters are designed to be balanced, meaning there's no residual delta V or force on the spacecraft, in general, it's not perfect. And we saw something at the order of 0.02, 0.03 millimeters per second, and we need to take that into account, particularly for prediction forward. And then also, of course, we need to model our maneuver TCMs to, that we go to the right place. Now, so that's the dynamic model, but also you have to make this measurement and you have to correct for a lot of things. And so part of this measurement model is, where are the stations? We know these to a few centimeters, which also we have to include, for instance, plate motion, tectonic plate motion, tides, tidal loading, all these things are modeled. Of course, we need to have a very good model for the Earth's troposphere and wet. And we basically use actually GPS to determine these models, and they are generated for us every day. Also, the ranging measurement is not perfect. So they always do a calibration, but it's not perfect. And we get about a 1 or 2 meter error, so we need to model that as well. And of course, the Earth orientation, we need to know how the Earth is oriented when we make our measurements. The other thing is, which is very important, is the quasar positions, because we are actually deltaing off the quasar position. So if we have an error in the quasar position, we have an error in our position. So we need to model that. And then finally, there is actually solar plasma. Right now, we're kind of in a quiet period, even though we could see some solar plasma and effects on our measurements, and I'll show that a little bit later too, that affect also our accuracy. All right, so that was basically my intro. So now let me get to what actually happened. So we were all ready to go for the first launch opportunity at 11:50 UTC. And about 20 minutes before that, we get actually a 4.2 magnitude earthquake in Los Angeles. And the thing is, we are actually what's called part of a launch hold criteria, meaning like we need to be operable in order to go. So we were scrambling there for 20 minutes, like are all computers working? Nothing is damaged? But we came very rapidly to the conclusion that even though we felt it was a pretty good jolt, we didn't have any damage. So we went ahead to launch. So everything went well. And we got a hyperbolic injection at 12:43. And at 12:47, the spacecraft separated from the launch vehicle. And you can see that on the left. It's actually happening in the dark. That's why it kind of is a dark image. So everything went well. And the reason why we didn't turn on the transmitter was because we wanted to wait until we were in the sunlight so that we get power out of the solar panels. So once we got out of the Earth's shadow, we turned on the transmitter. And we saw saturation at the DSN. The signal was so strong that that they had trouble locking onto telemetry and things like that. But within 1 second, we entered into safe mode, and it turned out a cooling pump was having a problem. And it didn't really have a problem. It just kind of thought it had a problem, and it decided to switch it off. And because of that, we went into safe mode. And what happens in safe mode is that the spacecraft even pumps more power into its antenna to talk to the Earth. So we were in this saturated situation for a couple of hours. You can see that it took about 3 hours before we finally got two-way Doppler, meaning like that we can actually transmit up a frequency and then it actually transpond sends back to us. And during that time, believe it or not, we were using basically what you do in GPS. We did one-way difference. So we had data from Goldstone and from Canberra, and we just differenced them. And then what you do is you difference out the oscillator that is on the spacecraft, and we actually got very good geometry information, and then this allowed us actually to do an orbit, and we decided that everything was okay with the launch. So finally, we exited the safe mode at about that was about 8 hours later, and then also we got actually ranging. But since we had such a good injection, and I'll show you that in a second, everything was just fine. So before I go on, I'm going to show a lot of plots that are called the B-plane. And the B-plane that's how we normally show our navigation results in. And also it's used for targeting, maneuver targeting to actually when you're on a hyperbolic approach. And you can kind of think of these B-plane parameters as kind of like the equivalent of Keplerian orbits, orbital elements, which are nearly constant. They're not quite, but they're nearly constant. And this allows much easier, anywhere you are in the orbit, you can compute these quantities and you more or less get the same thing. But the main thing for us is that any change that we do, for instance, we make the maneuver twice as big, we would see a twice as big change in the B-plane. So things are linear. And this really helps us to interpret, are we doing the right thing? Is something strange? But if you have to do this all in a non-linear hyperbolic trajectory, it's really hard. Just to kind of get a little bit into the B-plane here. So here is the how we approach Mars, and this is in the orbital plane. And we come in on a hyperbolic trajectory from this asymptote. And then we actually, if we would not hit Mars, we would actually just go nicely around and exit again. So the plane that we build is actually a plane that goes to the center of Mars, and the incoming asymptote is actually perpendicular to that plane. So basically, it's kind of like as if you're from far away from Mars, you're looking at it, and you're just looking straight at Mars. Now, then we have to choose another direction, and for that, we choose the Mars equator. And that's in that plane. And the reason why we choose that is because that helps us to kind of, to see relative to Mars where you're going to go. You can see actually the latitude and longitude as that. And then, in order to complete this frame, you get this R vector. And notice it's down. So you'll see that the numbers in the plots are actually going up as you go down. And it's negative when you are going up here. So what we do then is we take our, our state, our position of velocity, transform it into the B-plane. And this is actually the B vector here, which is just in the B-plane right away to the, and we're basically here, this is what's called V infinity. So when you're at infinity from Mars, the velocity, you just project that out onto the plane, and then you get, we also have an uncertainty ellipse associated with that, and that's what we plot here. And that's what you kind of see, is that we're looking in this plane. And then there's, of course, a direction perpendicular to this plane, and that's what we call the linearized triangle flight. And so this is kind of how we assess, well, how well, our targets are defined in this plane, and also we compare how well are we doing with that. So for Mars 2020, what does our B-plane target actually look like? So if you look in the upper left, you see actually all of Mars. So this is now in that plane, and here's the Mars equator. And you can see that here is, the red circle is actually what we call the impact radius. So if you go inside that red curve, you would actually impact the planet. Or in our case, we're trying, of course, to land. And our actually target is right here. We're about 18 degrees north on Mars. So if you then zoom in, here's actually, again, the impact circle. And here's our little targets. And I zoomed in again on that here onto the right. So now you can see that actually these openings of the tube that I mentioned earlier, the garden hose, are actually rectangular openings. And what these boxes here actually represent is, so let me first say what our requirements are. So this line here, that actually is if you come in at an entry flight path angle of minus 15.5 degrees. So if we're perfect, we would be right on this line. But, as I said, we need to be in a certain corridor of plus or minus 0.2 degrees. So that's what this corridor is. So this is one part of the opening, and cross track was 5 kilometers. So here's our target. So this needs plus or minus 5 kilometers. Now, and when I say this is at entry. Actually, in the B-plane, it's about twice as big. So anybody who puts a ruler on this plot goes, okay, this is about twice as big. Well, that's the reason why it maps to the B-plane. So this box here is where we need to go through. However, as I said, the EDL folks, they really want to know much more, even more accurate than that. And they actually came up with their own box and said, we want that uncertainty ellipse. If the center of that ellipse is inside that green box, we will not do any more maneuvers. We said we're good enough, we're going to land. Now, if the spacecraft is not quite healthy and you can't do a maneuver, if we're inside the yellow, it's kind of bad forward to see. If we're inside that, we're not doing any maneuver. Now, then we have also what we call a Hail Mary maneuver, 9 hours out before landing. And if something's really wrong, then if we're inside this box, we would not do that maneuver. But if we're outside that box, we would do that maneuver. And as I said, it's the center of the ellipse that matters. So part of the ellipse can be outside that box. They take it, when they made this box, they took into account kind of the sizes of the ellipses that they expect. So this is kind of where, so you'll see a lot every time these green and yellow boxes and black boxes in the plots that I will be showing going forward. Now, before doing that, or let me go back here for a second. You notice, by the way, that the corridor is actually very small in flight path angle, but not in cross track. They make really very long boxes. They allow us a lot of freedom there. And the reason for that is we're flying actually with entry guidance. And that's a paradigm shift from how we have been doing things. Before, we would fly basically most landers, except MSL in March 2020, as ballistic entry. What that means is that the center of mass of the spacecraft, the entry vehicle, is right on the center line. So there's only drag on the spacecraft, and I even call it kind of the flying brick. It just goes and it lands. So what is important is that you really hit the target and you hit that flight path angle so that you go, because you can't control anything. It just goes down and it lands where it lands. So you want to get as close as possible to the target. However, for March 2020, we actually, just before we get to the atmosphere, we actually drop off some balance masses, which make the center of mass go a little bit off that center line. And what that does is it creates lift on the body. And that lift is then used to actually start flying through the atmosphere. And you can see here, this is the picture looking from the back. So here's that lift vector. And in general, they can control, basically, they can move this or rotate this lift vector around depending on where they are. But we start off before we hit kind of like on this angle like this. So once you hit the atmosphere, one of the first things that happens is just when you start actually moving in this direction, because this component of the lift vector right away moves you cross track. This actual component actually controls if you get closer to the target or further away from the target. But basically, this is coming in for free. So all you have to do is, if you need to take a little bit more cross-track error out, you just wait a little bit longer while sitting in this orientation, and then you flip over to the other side. And this is what's called a bank reversal. And basically, we do this a couple of times back and forth. So you fly kind of like in a wavy motion to the ground. But because of this, it allows you to fly out any errors that you might have had at the delivery. And this is why we call it sometimes TCM7. And so the importance is for March 2020 is know exactly where you are, and then you can use with this guidance system, you can fly yourself to where you are. And that was quite a different paradigm than what we had for the other missions. So the important thing is here where you are, not hitting the target. All right. So now actually I'm going to show some of the results from flight. So here in the lower left, you can see actually the here's Mars again, and this big red ellipse is the injection uncertainty ellipse for the launch vehicle. And by the way, all the ellipses I show are 3 sigma. That means like we believe that we're somewhere within this 3 sigma ellipse statistically. And so then I show here more the blow up of this area here. And you can see here's our launch target again. And we actually injected right here. So we had actually a very good injection. The launch vehicle did a really great job. And then the first thing we wanted to do was right away, real quickly, was test our thrusters, and particularly in the lateral direction, which is perpendicular more or less to the spin axis. And the problem was we couldn't design that while we were in flight. So we made this before launch. So we actually just said, okay, we want to go from here to here. We basically looked kind of like, well, we're going to kind of roughly inject here. So this is the direction we want to fly. But we could have ended up here, and then we would have gone here, which would have been fine. We had the propellant to do that. But you can see here, this is how well we determined at the time of that we did this maneuver. And you can see where we ended up. And you can see after a few days, we actually had to start designing the first TCM. And this stands for data cutoff, meaning that we take all the data of a particular time, which in this case was 9 days before the maneuver. And then we would design the maneuver. And you can see that there's a little green ellipse behind this. That was originally after the maneuver. And then here we actually determined where we were. Then we targeted this position. And you can see here's the entry target where we want to go, but we did not target there because of all the reasons that I said earlier. And you can see that the ellipse here, this green ellipse, that the blue ellipse is larger. And the reason for that is there's all these errors that you have in when you execute a maneuver. So that actually inflates and that actually propagates all the way out to Mars. And that's why you get a bigger uncertainty. But you can see after about 45 days later, when we did our TCM2 design, you know, the ellipse already shrank a lot, and this is where position. And again, you can see that we got very close. This was a very good execution of the maneuver. Here on the right-hand side, you see actually the linearized time of flight. So this is basically, are you coming in early or late? So in this case, we were about 6 hours late. So this, the LatCal put us a little bit closer to 6 hours, and then most of TCM1 took out most of it, and we were a lot closer to our entry time that we wanted to be. Because as I said, remember, we have to get there at the right time, otherwise, you know, we can't get into the opening of the tube. So then for TCM2, so here again is the target where we want to go. So we actually, again, designed at this time the maneuver, and we actually executed. And you can see TCM3 is that little purple ellipse. And this is because there's a lot of time between TCM2 and 3. And we really determined very accurately what we have. But again, you can see the maneuver executed very well. It was very well done. And here you can see, again, we reduced the error in time. But then you see between actual, when we got there and actually the last TCM3 DCO, we got a little bit more time change. And that had to do with the fact that we're doing a lot of turns and we're doing lots of calibration turns. And they are not executed perfectly. So we're getting a little bit delta V error, and that's what causes some delay of about 500 seconds. So then for TCM3, we actually were allowed finally to target to our target, and that's what we did. And you can see here, again, the ellipse gets larger because of the execution error. So we could have ended up anywhere in this ellipse, which is a pretty big ellipse after TCM3. We're still about 14 million kilometers out from Mars at this point. And, you know, so there's still time, basically it's 2 months before landing. So there's a lot of time still that the errors can grow. But we just were lucky because we ended up, and you can see it here, here's TCM4 and TCM5 DCO. We ended up right away in the green box. So we were done. We didn't have to. And again, because we are, you know, not targeting, really trying to get to the target, we're trying to give knowledge or, you know, where we are exactly the best here. That's why the EDL team decided this was just fine. We're not going to change anything anymore. We're just going to use that. So then here, just a kind of a little table here to show in terms of sigma, you know, we assume a certain error, Gaussian error, and you can see they were very small. These first two were uncalibrated. So you can see we calibrated them and we did really well. So because of that, this was the first lander mission that it only did it in 3. Normally, we always need one more at that point. So so you saw some solutions here, and those are the baseline, but we do many variations. And this is particularly, you know, for GPS, when we also have Doppler range, but we have 3. We have Doppler range and delta DOR. And you can see if you just, for instance, look at some of the, if you only use one data type, for instance, this one here, this big guy is range only. So you can see, and by the way, here's our baseline, that little purple. So you can see that if you just range only, you're not going to get there. You're not even close. You're not even in the green box. Plus, you know, your uncertainty is really large. This red ellipse is just if you just use only Doppler. Again, you're not close. Again, they encapsulate the solution, but again, it's very large. And then here you see this ellipse, this kind of greenish ellipse, is actually when we only use Doppler and range. And again, you see it's a lot better. The two help each other, but still we're not anywhere near close into the green box. However, including delta DOR, then you get this nice little ellipse. And so really the delta DOR is really the measurement that really helps us to get this high precision navigation there. Now also, so that was basically changing different data types. Here we're changing all kinds of dynamic parameters. We're changing, you know, because we're estimating for media corrections and we consider them or not. We're estimating all kinds of variations, but it's all, they're very consistent and they're all nicely in the box. You see they're kind of all varying along the semi-major axis of this ellipse, and that's where you expect the uncertainty to be. So basically, when the management saw this, they say like, yeah, this looks good. I mean, there's no reason why we should do anything more. So we canceled TCM4 and we wrote it in. Now, the other thing that we do is we actually have different arc lengths, meaning like how much, over what time interval do you fit the data? And at the end, we actually have more. You see with F, we had G, H, and I, and J. We have a lot more arcs. But I just wanted to show something here because this is kind of what we showed during our approach. The F arc starts on 18th of December. This is actually 2 months before landing. And the G arc starts at January 12th, about a month later. And I'll come back in a little bit why we chose this. But to show here, this is actually every day you show the solution that we have, and then we show the uncertainty ellipse. And you can see here on the F arc that we're kind of like walking in, we're walking. But on the other hand, every new solution always kind of fits in the previous solution. So the uncertainty shrinks, but there's also motion associated. So this is what we call statistically consistent. Remember we advertised for this solution here, the outer one, that we're anywhere in here, can be anywhere. So this is okay. But on the other hand, if you show this to the project management, they kind of get worried, like, are we going to walk out of this green box and we're have a problem now? And I'll show you in a little bit why this was. It shows it was subtle, but it was. But on the other hand, we were confident this was fine. And you can see here the G arc doesn't have that problem. In the beginning, you see it walks a little bit, but that's because we have very little data. But then it also nicely clusters, and you see they show exactly at the same point. So they converge to the same point. So we always end up there, but the point always is, remember, they want us in advance to predict. So the GR did a much better job of predicting where we were going, but in terms of showing more stability, not a better job. And so you can see here, until the February 10th, 8 days before landing, we were using these solutions. And the reason was because they're so much smaller, the uncertainty ellipses. But once the GR kind of caught up and had enough data that the uncertainty shrunk enough, we switched over to this. And this is what we used actually for the last few days and use it for all our decision as we were going in. So then the question is like, well, why was this walking? What was going on? And for that, I have to show you a little bit our Doppler residuals, arranging delta door residuals. But basically what you see here is the F arc, which starts here. It's all the way this whole length. And then we have here the G arc. And also what this shows, actually, everything in the gray area is actually prediction. That's not actually adjusting the trajectory at all. It's just predicting forward. Also, you see, it doesn't look like it's nicely mean zero. And the reason is this is what we call a pre-fit, meaning like we're actually adjusting for some corrections, but we want to see kind of what's going on in the measurement. So purposely we leave that out to kind of demonstrate. And as I said here, for instance, you see a period where we kind of went up and went down, and another one here where we went down and came back up. And these are periods where we saw increased solar activity on our measurement. On the other hand, look at the data weight we're using. It's well within the noise that we're using. But on the other hand, systematic errors like this can really pull you off a little bit. And on top of that, in Madrid, they had snow. And for 5 days, they could not move their antennas anymore. So we didn't get any data from Madrid as well, which also kind of added some systematic into the measurement. So this was Doppler. And then here's range. And you can see the range is getting noisier as you get further out, and that is expected. But you can see this kind of like systematic wiggling back and forth. It's a little bit bigger. Here you see our data weight. But again, the snow here in Madrid is not helping. And again, some of this is also solar activity as well, but also some other stuff that we are still looking at what that might be. But what really was driving the difference between the F and the G arc was these three blue delta doors. You can see they're kind of hanging high a little bit. And I told you, we're very sensitive to the delta door. So once we basically went to G arc where we don't use it anymore, then after that, everything is nice and flat. And you can see even here, this was the F arc, again, the residuals. These blue guys were pulling us off. And the reason is we had to correct for what was going on here initially. And also what happened is here's that Madrid snow. We switched it from one quasar to another quasar, and we didn't get any more measurements in between. So it is always like, never fails. Murphy's Law strikes. When you really want a measurement, you don't get it. So, but anyway, in the end, you always get where you want to go. So as I said, the importance really was to get the best knowledge on board. And these are those OD solutions that I used for putting things on board. So the first one we put on board was EPU 1, which was 7 days before landing. And you can see here the red ellipse, and the center actually we put on board. And then about 19 hours before landing, we actually did 2 more of these solutions. And this is the one that we actually put on board, because notice, by the way, there's a little bit of a southerly direction in this in these solutions. So we were assuming it may go a little bit further south, and our shorter arcs were also kind of indicating we may be further south. However, when we finally reconstruct and landed, we went a little bit further north, and that's always because people the management was asking me, "Do you know where you're going?" And I'm like, "If I knew, I would be in Las Vegas," because you really can't predict where you're going to go. But you see it's moving nicely along this uncertainty axis. But the interesting thing is also that the first one we put on board was slightly better than the actual second one. So as I said, we needed to know where Mars was. You know, we really don't know where it is until about 20 hours before. So what we did was there's actually several orbiters around Mars, and they actually have still ranging capability. So what we do is we just range to the satellites in Mars orbit, and with that, you know where the center of Mars is. And what you see here is in the line of sight, we had about a 15-meter residual. So we knew all along to about 15 meters where Mars really was. And you know, the plane of sky, of course, we can't measure, which is that the perpendicular to the line of sight. The covariance is telling us it was about 100 meters. And we had actually one run later, which was before I made these slides, and the adjustment was about 60 meters overall. So Mars, we really knew very well where Mars was for that going on. So to summarize the whole navigation, here you see all the TCMs and their sizes. So you can see we had one big maneuver, the 1.9 and the 0.5, but after that, it was really small maneuvers that got us right away where we needed to go. We only used 9.1 kilograms compared to our 45 kilogram allocation. We did our 2 EPUs, and you can see here the performance of those that with the reconstruction after the fact, we were only 141 kilometers off, meters off in with respect to actually what we reconstructed, and about 150 meters off with the reconstruction. And you know, our requirement, as you recall, maybe it was 2.8 kilometers. So we did a lot better. And we'll show, in a second, I'll show you even our solution was better with that as well. So we were done, right? We delivered. However, as the spacecraft going through entry, descent, and landing, it's still sending out Doppler signals. And we actually had the requirement that we could follow that because, like, for instance, here, we can see some of these events happening in our Doppler data. And for this parachute deploy, they were really interested about because, you know, all those folks that you see in that control room, they're looking at what commands were sent, not if it actually happened. And we actually see the velocity change because the parachute deploys. So, and here, for instance, you know, we can also see when we hit the atmosphere as we are flying through the atmosphere. So that was our last task. And then just to get back to where we are, you know, you see here, once this point, we can't really see this anymore in our Doppler. But once the heat shield is dropped off, there's a camera underneath that will actually take images of the surface, and it will use what's called terrain relative navigation. And what it does is basically it has a hazard map on board, and it determines from all these landmarks that it sees where it is over the surface, and then it actually diverts here. You can see that to a safe location on Mars or in that area on Jezero. And when this actually opened and it got its first image, it was only about 120 meters off from where it predicted from going, just taking the IMU measurement all the way going through landing here. So that was also good news for us. I meant, like, you know, we had a pretty good prediction here in space, what we gave to the spacecraft. So what I'm going to show you now is, like, what did the Doppler really look like during that entry, descent, and landing? And this is the top plot shows actually where we actually modeled nothing. So we modeled basically just no atmosphere, no EDL. We basically flew through Mars. And you can see here, it's 120,000 hertz, kilohertz, 120,000 hertz. This is about 4.6 kilometer change in velocity in 7 minutes. This is where, you know, why we call it the 7 minutes of terror. You know, a lot of things can go wrong and you have to cut, you have to hit the brakes hard. But you can see here in the vertically, all the events are marked. And you can see in this plot, well, you can kind of see, yeah, we hit the atmosphere here, and you can see kind of the chute deploy, but not much else. So what we also had a trajectory where we kind of use a simulated EDL trajectory, our best estimate of what could happen. And then you can see it's the same timeline here. You can see very nicely that first that it flies in one direction, then you get the bank reversal, it comes in the other direction, comes back one more time, and then it flies basically straight. And then this was, of course, a sigh of relief for everybody when we actually saw this happening. And when I called on the VOC, I said, you know, parachute deploy. And they were very happy because, you know, we knew at least that work was inflating a parachute is always a nail-biting event. And then you can see some other things. This jump, I don't know at this point. We're looking into this, what this actually is, why there was a jump there. We don't know yet. But you can see we don't see much of the rest until they touch down. So with that, the circle is round, you know, we are back to landing. So we started I started in 2012 working with the landing. And then it's very nice to see in 2021 that we actually landed, and, you know, at a very nice place. And the other thing that I wanted to say was that this was our first look around. And the TRN, which I described, actually, it had like several wedges it could go, and it went to the very edge of that wedge because that's what the safest place was. So it flew another 800 meters or so to actually get to a place. And just around us, it's all not nice stuff to land on, but we were in a nice little spot where everything is fine. And also, they're also planning to fly the helicopter there. Yesterday, they dropped the debris shield from the helicopter, and now the rover is driving to the site to actually drop off the helicopter, and hopefully in a few weeks we'll start flying. Now, there are many pictures and videos. I really encourage people to go there to this website where you can see data. And by the way, as soon as images come to the ground, they will be posted there, so you can look raw images right away, and also the latest news and videos. So with that, thank you, and I'll go ready for questions.
Okay, well, thank you very much, Gerhard. That was fascinating. I can give you a round of applause. People hear me. Please try to imagine 600 people all clapping for you right now.
Right.
So we have about 15 questions. If you can stay, I think we can just go through them all because we don't have a hard cutoff time. Is that okay?
Yeah, that's okay.
Great. So, and I've tried to arrange them in order of like navigation questions first, and then some sort of more general interest questions later. And so let's just jump in. I did want to observe. I noticed you didn't need TCM 4 or 5 in the end. So I think you scored an eagle on this par 5.
That's correct. Yes.
Fantastic. Okay, so first question, can you explain more what the F arc and G arc are?
Okay, what the F arc and the G arc are. Let me use this here. It's just a length of the period of time that we fit tracking data over. So in this case, it's here. So it starts here at December 18th, and it goes all the way to, in this case, about February 9th or 10th or something like that. And the G arc is just a shorter arc. So it has less data in it. And in general, when you do a least squares fit, if you can fit less data, in general, you get a better fit. So, but it's always a balance between, you want to have a long arc because that has history, but you want a short arc because you don't want to, for instance, be driven off like what we hear, these points here, that we were driven off a little bit by our solution. So that's what the difference is.
Right. Can you discuss how you handle the time delay between the command being sent and received?
Well, basically everything is programmed in advance, right? So everything, we're watching the show essentially. There was an 11-minute light time. So essentially everything is pre-programmed and we're just watching it. It's all basically watching it after the fact.
So even at the TCMs, you pre-program what you want to happen when it gets there?
Yeah, we send the command about an hour before and say, okay, execute at this time. Right. That's how it works.
Right. What inertial navigation systems were used and what were their technologies?
Now, for us, it's for flying from Earth to Mars. We don't use any IMUs, but on board, they actually used an inertial measurement unit. It's called, which measures angular motion and actually acceleration. And those are basically used by the computer to actually compute the navigation solution on board as it's landing. So that's basically what it's using. It's an inertial measurement unit. Right.
Okay. So how much does simulation play in the overall accuracy? So put another way, if you didn't do any course corrections, then where would you expect to arrive at?
Well, first of all, we have to do course corrections, right? Because we had to bias because of planetary protection. We were not allowed to target right away, so we had to do. But what we do is, particularly, we do actually simulate data. If we have data up to a certain point, we simulate data after that to see, what the uncertainty would be if we were getting all the tracking data that we were promised. So we do. It's a combination of the two. We mainly use that to initialize the entry, descent, and landing, and we did that on a regular. We did that the first time 6 or 7 days after launch. So we do, it's still a combination, but then in that simulation, we add in the ideal delta V to get us back to where we want to go.
Okay, thanks. And then sort of related questions, do you perform any Monte Carlo simulations before the launch to determine mission success under unforeseen circumstances, like the Madrid snow when no ranging or Doppler is available?
Right, yeah, in general, we do not do the Madrid, that we don't simulate, but actually, remember we have to make sure that we have enough propellant. Those are actually Monte Carlo runs, and we do 5,000 Monte Carlo runs, assuming all kinds of different errors and making sure that for all situations we have enough propellant on board so that we can reach the opening of the tube, basically the target. So yes, we do run Monte Carlos.
Great, thanks. So next question is the 2.8 kilometer error budget all navigation error, or is some of it due to the uncertainty of the orbital elements for Mars?
It's everything together, all error sources, including the planetary ephemeris, yes, for Mars.
Yeah, and by the way, so what about how much is the contribution of the planetary orbital error?
Well, that's what I told you, right? We determined it to be about 60 meters after the fact. It was 60 meters off.
Right, okay. Next question is, how much three-way tracking was used from the DSN?
Only at launch. After a few hours when we got some two-way, we used a little bit of three-way, but a few hours after that, we didn't use any three-way.
Okay. How long are the Delta Door sessions, and how often do you switch between observing the SC and observing the quasar?
The session in total is about an hour, and we look 3 times. So we go 3 times between the quasar and the spacecraft and back to a quasar. So we do that 3 times.
Okay, thanks. And how did you range to the satellites in the Mars orbit? Was it done from stations on Earth?
Yes, it was the same DSN stations that we used for Mars 2022. Because, before, the orbiters were at Mars, they had to fly to Mars, and we use the same principles there of Doppler and ranging. So it's a capability that's on board. In general, you do not need ranging once you're in a Mars orbiter because, the dynamics of flying around a planet is good enough to constrain and get you good enough information. But if you want to know what Mars is, you actually have to do ranging. And actually, we didn't do this for Mars 2020 for the last 6 months, but you can also do Delta Door with the orbiters around Mars. And that also gives you information about the component perpendicular line of sight.
Okay, and then we just got a question in that's kind of related to that. Can you give a little bit more detail on the Delta Door positioning with respect to quasars, and how precise are quasars' location, and how many do you use for differential corrections?
Right. So you saw the Delta Door measurement. It's about, I think I had it on my slide. It's 2.4 nanoradian. Let's see if I have it here. Yeah, 2.4 nanoradians. So that's the accuracy that we can get. And the quasars are known to about 0.5 nanoradians. Something, maybe a little bit better than that. It's a little bit better than that. But there's other error sources. This is the whole budget. There's many other error sources in that. But the quasar locations are pretty well known. They've been observed for a long time.
Right. Okay. So I'm going to go on to so those are like specific navigation questions. We've got some more hypothetical questions, and then there's obviously some coming in as we speak. So I'll get to those more chronologically. There's obviously tremendous interest in this. I can see the activity here in the Q&A. So just some hypotheticals. So would a tracking station on the moon give greater accuracy in the spacecraft position on its journey?
Not much, because the only effects are really is the troposphere and ionosphere. And because we now have such a dense GPS network, these models are pretty good. They're actually, we're actually going to do a study with some of the GPS JPL group to actually see if using 200 GPS stations or a GLONASS or no GLONASS to see if it makes any difference. And so far, we're not seeing much difference. So the models are just very good. So I don't think we would get much benefit from having a station on the moon. Actually, I think it would be maybe a little bit less well known because you need to know the attitude of the moon very accurately, and we don't know it that well. We know it, as we do on Earth. So you would need to have a whole network on the moon to just establish what is the actual attitude of the moon. So that may actually be making it a little bit worse. So.
All right. So I know there's a lot of people on this, attending this webinar who spend a lot of time dealing with those iono and tropo errors on Earth. So it's nice for them and me to know that all that time somehow contributes to getting to Mars. So,
right.
That's great. Would establishing a GNSS constellation, which I guess would be an MNSS constellation on Mars, be of significant benefit to future missions?
Yes. Because remember, as I said, there's no GPS on Mars. Because then once you get below the altitude of the GPS satellites, right, then, or I guess MPS satellites, then you would actually remember. Then you get relative positioning to the planet. That's basically why we're lacking for most of our flight, is that we have no idea really where Mars is until the very end. So it would definitely improve things a lot.
Right. A couple of electromechanical questions. What was the thermoelectric generator used for?
That's our power source. We have no, there is also solar panels on the cruise stage, but once the rover is on the surface, it's the single power source. There's no other power source for the rover. So that's what it's for. So
it's charging the batteries all the time?
It charges the batteries, correct. And then it's used for everything.
Right, great. And what happened to the 36 kilograms of unused propellant?
That's somewhere on Mars.
Oh,
the cruise stage burns up. It gets popped off to about 10 minutes before we hit the atmosphere, and then it just burns up. In that, you may remember in that image here where I showed that you get that cross-track control. What it also allows us is to move away from the cruise stage, so that if we hit the atmosphere before the cruise stage, that we don't hit it back as we slow down. So the cruise stage, basically, this is also designed to basically avoid the cruise stage behind us, but it burns up in the atmosphere after that.
Right. Okay. So just a non-technical question, but if someone's a middle school student, how do they get from there to your job?
Well, I can tell you, I studied aerospace engineering. So after in college, and then in my case, I studied orbital mechanics. That's how I got here.
Right.
And also the other thing is, my advice is to students is try to find this. This is what I did. I actually went to a professor that actually worked in this kind of business, so that you and then what that allows you is you can get to meet people at JPL or other places, and then they get to know you, and then maybe you can do an internship. JPL has internships, so then you can sign up for those. That's the way to go. Get your name out there, talk to people.
Great. Okay, so we're going to get back to some more specific questions that are rolling in, but some general interest things, and maybe this is something you did along the way in your studies. Is probably not recently. Is can you explain the relativistic effects in a journey to Mars and on Mars for a person? So for example, if I travel to and live on Mars, will I grow older or younger compared to my twin back on Earth?
Yes, but it's very small. It's very small effect. But basically what happens is we do actually take relativity into account, because, if our equations of motion, this is a little bit of a technical thing, but if you take F equals ma, we actually on the force side actually correct for the fact that there is actually relativity. So we don't do exactly F times A, but A is like corrected with it's small, it's not that much. But it makes a difference. But it's a small effect. But
if a person actually did it, do they get younger relative to Earth because of the speed, or older because of the different gravity?
I think they go a little bit slower, right? So they get less old. I think if going to Mars, if you live on Mars. But on the other hand, don't count on it, because it may be a few seconds. That you gain.
Yeah. Right. Okay, so back to some more specific questions. How long does practical things you might actually be dealing with? How long does it take you to crunch a navigation solution? So for example, if the spacecraft shut down and you had to restart the system.
Well, those are kind of two different questions, right? I mean, for us to crank, we get, in most of the cruise, we do it once a day, but in the end, we do it every 15 minutes. So every 15 minutes, we can crank our solution if we need to. Restarting the computer, that's a matter of hours on the spacecraft. We actually had to do that when we got into that safe mode. We had to reboot the computer for that reason, to get it back up. So it takes a few hours.
All right. So this is a real thing, right? Not just hypothetical.
Right. No.
Interesting. And then related, did you develop any of the navigation algorithms for the EDL phase? This is from someone who built the RAD 750 computer and is interested in how the programming goes.
No, I was not involved in the EDL part at all. So they only tell us, we only get that what I said here, right? They tell us, 1 second. We want you to enter here at this position and at that velocity. That's what we get from them. So, and then I'm not involved with this whole part.
Okay. All right, so I'm just going here to the most recent questions that have come in. I'll just do them in order. Let's see. Where and when do you stop spinning the spacecraft?
Oh, that's a very good question. So we spin it up just when the launch vehicle gets in, just before it separates, it spins the vehicle up. So it's actually starts, and it spins it up to 2.5 RPM, and then it actually separates. And then about a day later, we spin it down to 2 RPM. And then the spin down occurs about at Mars. It happens about, let me think for a second, about 8 minutes before landing. That's where it will, and then it will actually become a 3-axis stabilized spacecraft.
Okay. And then from the same person who's asking, is it possible to get a copy of the chart? So now, as I mentioned in the beginning, this presentation is being recorded, so these charts will be presented on YouTube and on ion.org website as part of a video, but I don't know if ordinarily you share them as PDFs.
Well, if you look at the bottom of my presentation, it has been approved for unlimited release. So if you want to, you can put it on your website, something like that.
So we could put the PDF on the ion.
You can put the PDF on ion.
Great. I think we'll probably do that, and then I think that'd be very nice for a lot of people. Next question: how significant of an effect is the solar plasma?
Well, you saw here, it's not that big for Mars 2020, but it is. Let me see this. So here it's. Can you see? You can see here. So it's maybe. Yeah, 5-10%. But by the way, we're kind of in a quiet period of the sun right now. Remember, it's getting bigger again. But the next missions, that will probably go and pick up these samples, hopefully, they're going to be right there, kind of at the peak or near the peak. So it will be a lot bigger probably for the next mission. So, but for us, it was small. It didn't make that much difference. It's just when you cut, remember, like we talked about data cutoffs, right? If you cut your data off right here, right, then you can see that you would pull your solution away. But then if you get more data points and you pull back. Right, so we would see suddenly we move a little bit in the B plane and then we come back. That's kind of where we call it systematic errors, right? But those are the ones that are really, you have to really be careful about that. Sometimes we downweight this here, for a while just to make sure that we understand what's going on. So,
right. You mentioned you don't know where Mars is until about 20 hours prior.
Mm-hmm.
How is this? I'm not sure what that actually means, and then the question. But I'll just read the whole question. How is this possible when prediction of celestial objects is so precise, at least from Earth?
Oh yeah, I mean, for an observer on Earth, you know exactly where Mars is all the time. But if you at tens of meters, you don't know exactly where it is, and that has to do with the fact. For instance, that it's called the N-body problem, right? But for instance, all the mass of all the asteroids which are between Mars and Jupiter, there's enough mass to perturb the Martian orbit. And the problem with the asteroid mass is it's not evenly distributed. It changes all the time as where they are. So you get kind of like a body with mass varying properties. And those are not very well known. And it depends how many do you take into account and how much you don't. And that's why there's still some uncertainty left in the Mars ephemeris, which is at the level of 100 meters or so.
Right.
So,
great explanation.
Yeah.
Yeah. Can Earth to spacecraft and spacecraft to Earth RF signals both be used for tracking spacecraft location in outer space?
Yes, if you have a very good oscillator on board, like what you have kind of on GPS satellites, when you have a really good clock, then you only need really a clock on board. You can do one way directly, and that actually there's some missions that have flown to actually test that. But for now, we are really using the two-way Doppler. Because that way you can eliminate whatever uncertainty is in the clock on board the spacecraft.
Okay. So by the way, I'm seeing questions are flowing in at quite a rate. So are you okay to keep going?
Keep going.
Sure. Okay, and people can stay on as long as they like. But for a moment here, I thought if they come in faster than we ask them, we'll be here forever. We'll see. So the question about why you use quasars for inertial reference frame to compare to Doppler.
Oh, because quasars are so far from Earth, right? Billions of light years, that basically, to all intents and purposes, they're a fixed point in the sky. It's not moving. Even stars kind of move a little bit. So it's because it is and it's so small from our view. So you can very accurately determine a very stable point in the sky. And if you do it with many, you can actually get a coordinate frame out of that. And that's basically why we use quasars. It's basically the foundation of our coordinate frame.
Right. For your Delta VLBI baseline, could you use GNSS observables at the reference station instead of stellar radio sources as a backup to VLBI?
I don't think so. I don't think so. I presume the question is, can you use GPS signals, right, to do this? And the problem is it's too close to Earth, I think. Yeah, that's not going to work, I think.
Okay. What are your opinions on using pre-trained machine learning models using data from one or more cameras for the final part of the guidance just before parachute opening?
Well, again, that is kind of like not part of what I work on, right? So I think I'm going to pass on that one. Okay.
What source did you use for your EOPs? Were they determined using the DSN or a different VLBI network?
I think, at JPL, we have one section one group that contributes to the International Earth Rotation Service. And this group is, we take the JPL version of that, but I think it's a combination of VLBI, GPS. I don't know what other sources they use, but it's basically, that's where we get it from.
Okay. This question is, what is the name of your OD code?
Monty.
Can you explain? I don't understand the question. I don't know. Can you explain?
Yeah, no. Our code is called Monty. It's spelled MONTE. And don't ask me what it stands for right now, but we used to have what's called ODP, which stands for Orbit Determination Program, but that was more used in the 70s, 80s. I used it a little bit myself.
Right.
But now and by the way, people are interested, you can ask for a license if particularly universities and students can apply for a license.
Computer code, the computer language that you use, is that?
No, it's not the language. It's actually it's the application, right? Okay. And and it's driven with Python. So you could use Python to call all these things. It's just import it in Python and then use it. So if anybody interested can go just search for Monty JPL on Google. I'm sure you can find it and what you need to do to get it.
Great, thank you. Good question. Do you use onboard AI ML? Okay, a very similar question to what before. To understand on which landmark to land. But I guess you answered that. That's not your domain.
Right.
Right. Okay. Why not use a star tracker?
For what?
I guess they mean for getting there in the first place, right?
Well, we have a star scanner because remember it's spinning, so you can't look at somewhere in the sky. So we scan for stars, and that's used only to determine the attitude of the spacecraft, nothing else. And also initialize the attitude before landing, but that's it.
Okay.
No other use.
What additional navigation instruments do you use in the event that DSN signals get attenuated?
We only have the DSN. That's it.
All right. Is the solutions delivery based only on the maneuvers DCO events, or are there also middle deliveries during the cruise?
Yeah, no, we do the design many times, and the data cutoff is just in general. The statement that I make all the time during these meetings is the OD solutions are stable, and the maneuver design is stable. That's what they'd like to hear, because keep in mind these maneuvers is a $2.5 billion decision, right? If you don't do it right, it goes wrong. So people are really worried. So they want to see a long history that everything is nice and stable and things. And particularly when you see a little bit of that movement that I showed at the end, right? That makes people a little bit uncomfortable. Is something going on that we don't know about, or, and things like that. So no, we do many OD solutions, and we do many maneuver designs as we go.
So do you feel the pressure there, like knowing every decision is billions of dollars on the line?
Right. Well, and it happens that the lab director and I went to the same university, so we know each other very well. So it's always he asks me lots of questions, so I can guarantee you that.
Right. When I was looking up your bio in advance, Gerhard, I came across TU Delft website, and they're very proud of you.
Well, that's good to hear.
So this is to do with landing, but maybe some of the, maybe just for general interest, what atmospheric resistance was considered during landing, and does it change as the distance to the surface changes?
Yeah, they have density, what they call density models. Yes, and this is one of the reasons also why we have guidance, because if the air is thinner or thicker than you expect, right, and we change that lift vector a little bit up or down depending where you want to go. So it is a function of altitude, of course, and it's just like on the Earth. So, but yeah, they have very sophisticated atmospheric models for that.
Right. And how does it compare to the Earth? Like, what's the density of the atmosphere compared to Earth?
I think it's like. It's like, I'm not sure, but it's like something like half a percent of Earth's atmosphere. It's not much. The problem with landing on Mars is, that the atmosphere is there and it gives you trouble when you come in, but there's not enough to actually land you safely. That's why you have to first go, use a heat shield, then you have to go on a parachute, and then you have to do a powered descent because you can't slow yourself down. If you land on the moon, for instance, it can all be powered descent. Right? Just keep the engines on and you just put you there. But on Mars, it's a very complicated thing. You have enough atmosphere to bother you, but you don't have enough atmosphere to properly land. So,
oh, that's interesting. And by the way, do you refer to, what do you refer to the atmosphere as? Do you call it air, or like what kind of name do you apply to?
I have no idea. I've never heard. Yeah, I've never heard. They always say atmosphere. The atmosphere. Right.
Well, I guess we'll have to think of a name. How precise was the onboard clock?
Yeah, we calibrate that too. Using the navigation solution, we calibrate that, so we know. And I think the error was something like 20 milliseconds at the end, which was within the requirement, was something like 40 milliseconds. So it was good.
Over the period of like 8 months?
No. This was how well we predicted what the clock at the time. Because remember, if you come in with 5.5 kilometers per second, right, 1 millisecond is 5.5 meters movement. So you have to. So that becomes part of the uncertainty position. Remember that 2.8, it's all in there. So I believe it was something like, or was it? No, wait, it was more like 13 or 14 milliseconds that we were off. So then multiply that times 5.5, and that's how much you were off in position. So.
Right. Okay. So in a future mission, this is a great question, I think. In a future mission, can you use the Mars ground equipment as landing reference in a way of two-way communication?
For landing?
Yeah,
because the next mission that we hope it will happen is that it will land very close, right, to Perseverance, because it's going to pick up the samples, and there we have to do a much better job of landing much closer. So, but it will not use it will do the same thing that Perseverance did. It actually uses a map, takes images, and then actually it gets more propellant basically, so that it can go further. Here we only flew 800 meters, but I think that one can fly to something like 8 kilometers to correct. Because they want to land like within a few hundred meters of those samples. So they want to be very close.
Right. So, okay, interesting.
So no, so the short answer is no.
So we've talked about quasars, but are you looking at pulsars as a navigation source in future mission?
Not that I'm aware of.
Okay. I know a lot of GPS geeks, including me, like the idea of pulsars because they like GPSs in outer space. But
right.
So we have to wait a little bit longer on that, huh? Okay. Yeah. So we understand this is not your area, but can you say something about the on-ground navigation on Mars and how that's performed?
Right. Well, basically, MRO has a camera on board which can do something like 30 centimeter resolution on the ground. So they basically have very accurate maps. And basically, once they have positioned themselves on the map, then it's basically they can just by looking around, remember they continuously take images, and then that's how they navigate. So it's basically avoiding all big rocks and things like that. But in order to get the map, you need to tie it. And actually, I'm working using Doppler residuals from when it's on the ground for the first 14 days when it didn't move, to actually determine how that map is tied to inertial space. It's called the map tie. So that's the last contribution I do for this mission. But the navigators on the ground basically use imagery to determine, and then they have very accurate maps. Because one of the big things was that they have lots of dune fields, and believe it or not, you would think a dune field is nice and soft, you want to land in it. Unfortunately, there's many places we call a trap. You can't get out. You can't get over the dune to get out. So that's why we have to avoid a lot of these places. And we actually kind of worried, if we hadn't steered ourselves away, we would have landed in the middle of a dune field like that. So it was good that we actually maneuvered away about 800 meters. So
wow. So yeah, kind of similar, related question maybe. Can you comment on lander spacecraft orbiting Mars first prior to entry versus direct entry?
Yeah, well, remember Viking, for instance, did that, right? And then the reason was Viking did not land right away is because they had no idea what was going on the ground. And they had actually cameras that were good maybe to like 100-meter or 200-meter resolution. And I remember actually the reason I'm in this business and want to work on Mars is because of the Viking landers. And when they landed, Viking 1, they landed and they saw this huge boulder. I think it was called Big Joe, but a few meters away from it. It was like, if they had landed on that, they would have been dead. So then they spent actually a lot of time waiting for Viking 2 to decide, well, where can we land and where to sit? And they picked an area and said, oh, it will be nice and smooth. And the first image that came down from Viking 2 was, it was kind of tilted quite a lot. And it turned out it was in a massive rock field. But the difference now is that, if you do not first go in orbit, you can land a lot more mass on Mars. And we now know from all the orbiters where it is, and we know what the hazards are. So that's why basically it allows you to land, Perseverance weighs about 1,100 kilograms, and then that's a lot more than if you could land, because I think the Chinese are right now in orbit around Mars too. And I think they're going to land something that's a few hundred kilograms. So that's the difference.
Right. So direct entry gives you can land a lot more mass.
Right. Exactly.
Interesting. What is the maximum range currently possible for Delta Door based navigation using 3 stations?
I have used, as I told you, I worked on New Horizons, and we flew by that Kuiper Belt object, which was at something like 35 AU, way beyond the Pluto orbit, and it still works. It becomes less and less effective because remember, the further you go out, right? But still, when you're that far out, it was something like 7-8 kilometers. So it's still useful. And particularly when you fly in that far outer regions of the solar system, there's no dynamics. There's no more planets that bend you. So you're in the middle of nothing. So it really helps, to kind of constrain yourself. And particularly that spacecraft thrusts a lot. So it's really helpful to have that.
So you can really use it throughout the solar system.
The whole solar system, yeah.
Right. Huh. Okay, you had mentioned that all the corrections are pre-programmed. What sort of redundancy is designed into the descent module, e.g. related to the terrain, relative navigation, for instance? Is there any sort of voting mechanism?
There is, and also there's 2 computers on board, and one is on a hot standby. So if one computer is having a problem, it will immediately switch over to the other computer, and the other computer will take over and land. It will have less capability, but it will be able to safely land. So yeah, that's been a lot of work has been put into that. So.
Okay. And was the mission scheduled to fly in the solar minimum phase to limit solar plasma and ionospheric effects?
Actually, this mission was originally scheduled to fly in 2018. We delayed by 2 years, for many reasons. Right.
So you're not paying that. So there's not such a decision. It's not entering your decisions then.
No, it's. Right. But mainly interested more is the storm season on Mars, right? There are periods where there's big storms, and we'd rather not land in big storms because there's much more density variation, and that makes entry guidance a lot more challenging.
Right. So you mentioned the dune fields and the rock fields. Are there any other surface structures that you recognize as hazards?
Well, particularly in Jezero Crater, there's that big cliff, right? There's a big delta, and there's a cliff of about 80 meters. So you definitely don't want to land. Also, slopes, just big slopes. We don't want to land on a big slope because then you might slide down, or so it needs to be kind of flat. But that's the main. Yeah. So rocks. We literally have someone at JPL counting rocks. They take images and then they count rocks, and so there's a massive effort. The guy that worked on that for at least, I know, since like 2014, 2013, just for this site.
Right. So. Rocks, slopes, and cliffs, I guess,
yeah,
right?
Yes, that's right.
Interesting navigation nerd question is, what coordinate frame is used during the interplanetary navigation phase?
We use a solar barycentric frame. Basically, it's centered in this in the center of actually we're using it's a version, but it's basically that's what it is. It's solar barycentric frame. So okay. It's that's the name. You can look it up.
Right. Okay. So this is a maybe after your job is ended, but the question is, did you use any visual inertial odometry at the last moment of landing, or do they use that?
No visual. By the way, the camera kept operating, that was used for the terrain relative navigation. So you can look, it has footage all the way to the ground. At the last image from the camera that shows like some dust settling, and you see the wheel and some pebbles and stuff like that. So it worked all the way to the ground. It was just not used anymore.
I see. Okay. And then you mentioned that you open source some stuff, but there's a question that like, did you use any open source contributions to this nav work, or can you comment on that?
No, we don't really use much open source, except for, like maybe making a presentation or something like that, which is not open source either. But you know what I mean. But no, for our navigation work, no.
Right. And did you use Kalman filtering or some advanced version of it, such as square root filter, etc.?
Yeah, we're using Kalman filtering. Yeah.
Okay, great. And there's another question about a star camera, which is why not use a star camera or camera to view Mars? I'm not sure if this is the same question as before about using Star Tracker.
Right. Well, the thing is, it's a spinner, right? It makes it a lot harder to use a star tracker. You need a star scanner, and they don't make those anymore because most spacecraft these days don't spin anymore. But right. Just an interesting little detail: the star scanner that flew on Perseverance was something like 30 years old. They started making those. They made one batch, and we just kept using them and using them. So we're almost out of star scanners now. So it's not a very much used technology anymore.
So dumb question from me. So the spacecraft's spinning all the way to Mars.
All the way to Mars. Yeah.
Right. A lot of interest in this. So this question, it sounds similar, but I guess it's different. So can you comment on possible use of Star Tracker versus quasars for navigation, reference, and guidance?
I'm not sure that completely follows. Star Tracker versus quasar, is that what I heard?
Yes.
Yeah, but I think, and maybe the question is like optical navigation, right? It's like, for instance, I told you about the Pluto mission. There we used optical navigation. We had a camera dedicated looking at Pluto and the moons, and we use that information in the navigation to determine where we were relative to Pluto. For Mars, yeah, we're not using it yet. As I said, it's complicated because we're spinning. And so far, this new the way we've done it for MSL and Mars 2020, we're getting incredibly good results, right? If you have a 2.8 kilometers and we're only 140 meters off, that's pretty darn good, I would say. So yeah, I mean, we'll go with what works, right?
Right, of course. Does JPL use Kerbal space program?
COBOL, is that what I heard?
It's Kerbal, Kerbal.
I've heard of that, but I have not used it myself or anybody in my team. So
okay, here's an interesting general interest question: has a prime meridian been defined on Mars?
Yes, they have redefined a new prime meridian. Actually, it's kind of interesting you mentioned. Remember, I'm doing rover positioning right now, and I get two coordinate frames, and there was a little bit difference, about 100 meters in longitude. And then I found actually a reference saying that yeah, we redefined the prime meridian of Mars. So yes, there is a prime meridian. For anybody who wants to interested, the reference is MRO 120D coordinate frame has a new definition of the prime meridian. So in case you're interested.
Fantastic. Can you tell us something about the navigation system on the helicopter?
I don't know anything about that. I don't know anything about that. Okay.
So just for the people who are still on, and there are hundreds, we're coming up to noon in California. There's about 4 questions left, so I suggest I'll go through those and maybe stop there, and that makes the whole thing an hour and a half, which seems a nice round number. Can you elaborate on how terrain relative navigation works?
As I said, basically what you do is you take an image as you're going down, and you use landmarks like rocks or cliffs or things like that to determine where you are on the map, literally where you are on the map. And then there's another map that's underneath that's called a hazard map, where we actually basically colored in, well, you don't want to land here, and there's a lot of red in Jezero Crater. It's a dangerous place. But there's also there's also blue places where there's a good probability you can land safely. And then basically once the TRN, that's why it's called terrain relative navigation, once it knows where it's on the map, then it will actually, because once it drops out of the back shell, the descent stage will fire, but it will also do a divert. And the reason why it needs to divert is it doesn't want to hit the back shell and the parachute again. But then it does an intelligent divert. It actually diverts to a region where it actually is safe to land. So that's kind of a nutshell how it works.
Great. Yeah, so we've talked about quasars a lot. There's a question, which quasar were you using?
Oh, I don't know the name right now. They always have these P1 for your father. I have no idea. I'll have to look that up.
Right.
I don't know.
Right. Okay, and here's I think a great question to finish with. So this will be the last question. What was the most challenging part of your role in the mission?
What was the most challenging part? I think the most challenging part is, to convey confidence in our solution, right? That we say, yeah, we really think we are here, and we, to do that, by the way, we had long sessions with we have what's called a graybeard kind of group of people, other navigators that are not involved, and they review our work, and you get really critical questions, and getting through that process, and kind of convincing them that no, things are all right, to really, that's kind of that's a challenge, to really make people feel good about, and as I said, I would talk to the lab director sometimes and to make sure that, that he's not worried that something is wrong, and convey to him that no, but we are confident in what we did. That definitely was a challenge.
Right. So. Very interesting. Well, thank you very much, Gerhard, this fascinating presentation. Thank you to all the people who attended, and the ION will have the video and PDF of the slides posted later today for you to share with people who were not so lucky as us to be here for the live thing. So just thank you very much, and we'll close there.
All right. Thank you.